morning all. Welcome to Tutorials with Eternity the Schoolboy. Today we'll take a look at chemistry. And I can remember vividly in our last class, we started with the structure of the atom. So there we focused mainly on the definition of atom and what John Dalton did in atom, the theory, John Dalton's theory of atomic, of what? Atom, right? So that's what, so we now, after that, we also looked at the modification and how the work of John Dalton was modified by the works of, can't say I want to be seeing your face like this, don't hide on that one. Sit like this, I want to see in your face. So if you are doing what I don't know, what I don't like, I will know. Shit like this. So we looked at what he did and how the theory was modified. And they didn't just modify the theory anyhow, just like that. A lot of scientists also worked on the what. In science, once you publish any work, a lot of scientists will start looking at it to see whether there's something they can make out of it, either to better it, mainly to make it a better one, or to see what else they can discover through your work, or any gap they can fill. So this is what scientists do. So when he published his work, other scientists started working into it, and they started seeing a lot of things that his theory could not explain. So that's what led to the what? Modification of Dalton's what? Atomic theory. So we look at the work of these scientists, especially when it comes to the structure of the atom, especially on the subparticles, because John Dalton's atomic theory did not even go below atom. He just said that the atom is smallest indivisible. He didn't account for subparticles like protons, electrons, and what? Neutrons. He didn't do that. It's from the work of others that they're able to do so. So, the work of these scientists, sit up. Chinwe, sit up. That's not how to sit in class. If you're tired, stand up. Don't sit like this in the class. If you're tired, stand up and walk around. That's the right thing to do. The work of these scientists, we want to look at the work of these scientists. Am I communicating? So what you do is this: we look at the year, their name, and what they actually did. So that's what today's lecture will be all about. Okay? Are we good to go? Good. So let's continue. Okay. Now let's look at the work of okay. In 1885, a scientist known as Roentgen, this is not English language, I don't know how they pronounce it. R-O, but I think I got it. But I pronounce it like in English word. I don't know whether it's English word anyway. R-O, look at it. I used to call it, even from secondary school, I used to call it Roentgen. That's what I call it that time, even till now. Maybe after I will check Google this thing, translate and see whether I can get it correct. I've not had time to do that. But just know that in 1885, that was 1885. In 1885, he discovered that when electron, high energy electron, before this time, there were other scientists that work on electron, okay, but they didn't actually call it electron, okay. They didn't actually call it electron. They were just calling it somewhere, called it cathode rays, But we'll stick to that. But I want to talk about this man discovered X-ray, okay. See what happened. What happened is that in 1885, he had a discharge tube that contains that from there high energy electrons were discharged. So this high energy electron collided. You know what is cathode and anode now, right? Yeah, good. Collided with what? The anode. He discovered that a radiation that is highly penetrating was emitted, and he called this radiation what? X-ray. He collided electron from a discharge tube, collided it with what? Anode. Am I completing? Now he then discovered that, but it's not just on high energy what? Electron. He discovered that a radiation was emitted that is highly penetrating. That's why X-ray can penetrate a lot of things. Hope you know. Highly penetrating was emitted, and he named it what? X-ray. Okay. Now, still after some time now, we go into other works, other scientists, but I'm taking it chronologically. What happened this year and what happened the other year? Now, in 1897, this happened in what? Hello? This happened in 1885. Let me bring the word. Please, as we write out this thing chronologically, try to look at, relate what happened before and what happened next, okay? Now, in 1897, J.J. Thompson, remember, Roentgen worked with a tube, okay? In 1897, J.J. Thompson also continued with that tube experiment. See what happened. It was already known before, scientists have already discovered that at ordinary pressure, gas do not conduct what? Electricity. Scientists had already discovered that at ordinary pressure, air pressure, gas do not do what? Conduct what? Electricity. But if the pressure is lowered, very, very low, gas can do what? Conduct what? Electricity. Am I communicating? Good. So, that's the first thing that have been in place since. Now, J.J. Thompson now utilized this idea of gas not conducting electricity at a very low atmosphere, and that is also using the tube this man also worked with. Okay, they now came to realize something. See what J.J. Thompson did. J.J. Thompson ensured that there is a potential difference up to 5,000 volts. He ensured that there's a potential difference up to 5,000 volts between the two electrodes in the tube. Now, that tube, that glass tube contains gas at a very low pressure. And because of this potential difference, see what happened? He discovered, of course, if you go to electricity, you know what happened whenever there's a potential difference, there's movement of what? Current. Hope you know. If there's no potential difference, will current move? No, right? There must be what? Potential what? Difference. So he created potential difference of about 5,000 volts inside the gas tube. Remember, glass tube. This Roentgen also used what? Tube. Remember, between the electrode, he created potential difference of about 5,000 volts, and they ensure that the pressure of the gas in the tube is very low, very low, to about 0.0001 atmosphere. Very low, about what? 0.0001 atmosphere. And potential difference is what? 5,000 volts. Now see what J.J. Thompson discovered. He now realized that the tube began to glow. Do you know what you mean by a tube is glowing? An example of glowing, have you seen a fluorescence tube? Fluorescence. Is there any bulb inside the fluorescence? Like the normal bulb, you know. That's an example of what? Glowing. That, as the fluorescence is coming up, is glowing. That thing is glow. That's what's called what? Glowing, okay? So when he maintained that potential difference at pressure of about atmosphere, 0.0001 atmosphere, he now discovered that the tube started what? Glowing. That's the first thing he noticed. He now said, okay, let me increase the potential difference to about 15,000 volts. So he increased it to about what? 15,000 volts. Look at what he observed. From glowing, he now realized that a bright green glow appeared in the what? In the glass. From just normal glowing, it turned to what? Green what? Bright what? Green what? Glow. It had taken a different what? Color. Okay? When he increased the what? The potential difference to about what? 15,000 what? Volts. Now, from that work he did, he now later on, from that work, now say that this glow in the tube is as a result of a ray that emanated from the cathode. Remember this one, electron. They didn't know the name that time, hope you know. Leave from cathode and collided with what? Anode, right? And X-ray was formed, hope you know. Now, this man also did something and now say that this ray coming from this cathode is one responsible for the what? The glow. He called it cathode rays. That was the first name they gave to electron before. Cathode what? Ray. That was the name they called it. He called it what? Cathode ray. And he said that, and this ray traveled in a straight line. In a straight what? Line. He called it what? The rays what? Cathode rays. Now, more work continued. After series of work, they now discover some properties of these cathode rays. They now discover some properties of what? Cathode rays. Remember I told you when one scientist work, and others will come and hope you know. They now started studying the properties of these cathode rays. What are the properties of the cathode rays? I think I'll mention one. It travels in a what? Straight line. That's on one. It travels in a what? Straight line. And one, it travels in a straight line. And it casts, number two is that it casts the shadows of any opaque object placed in its path. So as it's traveling from the cathode, it's coming out in a straight line. Anything, if let me say if you carry this something, any object now, opaque, not transparent or any opaque object you place in the path. By the path I mean in front of that path it travels, okay? If you place any opaque object in the path, it will cast the shadow of that what? Opaque what object? You see the shadow of the what? Opaque what? Object. So that was it casts the shadow of what? Any opaque, the shadows of opaque objects placed in opaque object. This is opaque. You are opaque. This is opaque. An opaque Substance is object, something that cannot, if you shine light on it, it does not pass through. Okay? Am I communicating? Like now, look up. This thing now, even though it's not that opaque, well, it's still opaque anyway, but you can see some things. But if you place this thing now in front of me, I cannot see you. But if I get glass, this glass now, or almaco glass, and place it now, I'll see your face. I'll see you. That one is transparent. Am I communicating? But opaque is what you cannot see through the an opaque object. So that's still, so cathode rays, if you place an opaque object on the paths of the rays will cast shadows of that what? Opaque what? Object. Now, the next one is that they are composed of only negatively what? Charged. So the cathode rays are composed of only negatively charged particles. That means they are negatively what? Charged. Have you not seen where electron started? They say looking at electron. Have you seen where it started? Good. Now, number one is that it can produce motion. It can produce mechanical motion. Okay? So it has the ability to produce mechanical what? Motion. So it can produce what? Mechanical what? Motion. Now that the last one I want to talk about now is very, very important. You know, these cathodes, metal, hope you know, are you aware? They can metal, hope you know. Even though we have platinum, but this one is metal. Now, this cathode, no matter the type of cathode you use in the tube, also no matter the type of gas you use in the tube, the cathode rays that will come out will always have the same nature, and the same charge to mass ratio. You know it has what? Negatively charged. Hope you know. That's what is called charge to mass ratio. That is specific charge. Charge of the particle over the mass of the what? Particles. It gives us the what? Charge to what? Mass ratio. So no matter the type of cathode you want to use, no matter the type of gas you use in the tube, what the ray that will come out from it will be the same thing, the same property, the same features, the same nature, and the same charge to what? Mass ratio. That means from there they now say that this is a fundamental particle. What means that every element or every matter has this what? This what? Particle. Am I communicating? Because no matter the type of gas you use, no matter the type of metal you use, the nature of the cathode ray will always remain what? The same. The mass to charge to mass ratio will what? Remain the same. So that is the last feature I want to talk about. So they realize that the cathode rays are identical. They are identical in the nature and charge to mass. Chinwe, you're not writing anything. What is it? Are you sure? Okay. I'm trying to say that the cathode rays are identical in what? Nature. And they charge to what? Mass ratio. Or you call it specific charge. Specific charge is equal to charge over what? Mass. So if you can simply say specific charge, you can now put in bracket mass, charge over what? Mass. So irrespective of they are identical in nature and the charge to mass ratio, irrespective of the what? The nature of the gas in the discharge tube and the what? The electrode used. Okay? So that's the point there. Now, So with this now, J.J. Thompson now say no. These particles are fundamental. When you say that something is fundamental, it means that the thing, almost everything has what? Everything you are talking about in question has that particular what? Feature. Even if you say something is a fundamental feature of human being, that means the whole human being has this what? Feature, okay? So if you say that is a fundamental particle, what it means that all matter have what? Have what? Electron. So that's what J.J. Thompson argued. And after that, J.J. Thompson concluded that this particle must surely be what? Electron. Remember I told you that some other people had proposed before, hope you know. So after his work, he now said that this thing people have been proposed, have talked about, must surely be the what? Must surely be the what? Electron. So after that now, he now check what is called the mass to charge ratio of the what? The electron, and discovered that the mass to charge ratio of electron. He discovered that the mass to charge ratio of electron is what? 1.76 times 10 to the power 11 coulomb. Put it down. He discovered that the charge to mass ratio of electron is 1.7 what? What did I say now? 1 point what? What did I say now?
765.
Yeah? Me say 5. Times 10 to the power what? 11 coulomb per what? Kilogram. This is charge to what? Charge over what? Mass of an what? Electron. Or you call it what? Specific what? You call it what? You call it what? Specific what? Charge. So J does not come up for specific charge of electron, that is mass to charge of electron to mass of electron is equal to what? 1.76 times 10 to the power 11 what? Coulomb per what? Kilogram. Coulomb per what? Kilogram. Coulomb per what? Kilogram. All right, let's continue. So this is what J.J. Thompson did on the aspect of electron. He now continued. He didn't rest though. Okay, you know I'm doing it chronologically, right? Now, so when the Roentgen did his work, 18 what? 18 what? 85. Okay, yeah?
Yes.
Rule what? Okay, yeah? Did I get it? That is what? X-ray, right? Then in 18 what? 90 what? 80 what? 97. JJ what? Worked on what? Cathode rays, good. Which he called what? Which he called what? He first called it what? Cathode rays now, then, and will you snow again? Near must be the electron, there they go since. Is it clear? Electrons. Now, in 1898, the same J.J. Thompson started again. He wanted to do something, but do I say that he didn't? Do I even say that he did not succeed? I don't know what I could call it, but at least he tried. So J.J. Thompson now, after talking about cathode rays and electron, you know now there's something you do now. You have to say okay, now let me push further. Let me now go into what atomic structure. He now started working on atomic structure to now tell us how atomic structure look like. So he now continued. J.J. Thompson, now after his work, he now said that atomic structure, we call it Thompson model of the atom. He now said that atomic structure is like this. Positively charged sphere. He said that is what? He said that is what? Something like this. Something like this. See what he did. J. Thompson said that an atom is composed of a positively charged spheres embedded see what J. Thompson told us. And that's how an atom looked like. After his work in 1898, right? He said that this is how atom look like. He said that the atom is what? Is composed of a positively charged what? Particles. Sphere. In which negatively charged, which are electrons, are what? Embedded. That's what he told us. This is what J. Thompson told the world. And this is how atom look like. Is it how atom look like? Yes. Like this. Okay, let's see now. Is it how atom look like? Chinwe, is this how atom look like? Is it how atom look like? People said that it's not. This is not how atom look like. But this is what J. Thompson told the world. And this is how atom look like. That atom is composed of what? Positively charged what? Sphere. This is a sphere, right? This is a sphere. Positively charged, in which negatively charged particles or electrons are what? Embedded. That's what J. Thompson told the world in 1898. We will still come up with something. After some time, Rutherford through his boys. After some time, I call them boys because they are his students. Okay, with time now, I'll prove to you what Rutherford did. I'll prove to you what Rutherford did through his boys. Called their names Geiger and Marsden. Geiger and Marsden. Who has heard of Geiger Muller counter? Okay, don't worry. We'll get there. Geiger and what? Marsden. I was just talking about what they did. From the work of Geiger and Marsden, this thing was proved what? Wrong. Okay? This thing was proved what? Wrong. We'll get there. Remember, we are taking it chronologically. If there is something is taken chronologically, you say which year? I'm not committing year by what? Year. Okay. Now, in 1910, another scientist, R.A. Millikan. R.A. what? Millikan. R.A. Millikan. If you are used to past question, You would have seen this Millikan up there. You must have seen Millikan's oil experiments. Who has seen that such before? Oil experiments. Huh? Child. Okay, R.A. Millikan's is called what? Is a popular Millikan's what? Oil what? Drop experiments. R.A. Millikan carried out what is called, named after him, oil what? Drop what? Experiment. Oil drop what? Jam, ask this question well. Where I can also ask it. Millikan's oil drop what? Experiment. So see what happened. Actually, R.A. Millikan in this oil drop experiment, he determined the charge of what? Electron. Okay? He used oil drop experiment to determine what? Charge of what? Electron. He actually determined the charge of electron to be what? Minus 1.6 times 10 to the power minus 19 coulomb. This is the charge of electrons. You want to sit up? Sit up. This is the charge of electron 1.6 minus 1.6 times 10 to the power what? Times 10 to the power what? Minus what? 19 what? Coulomb. This is what R.A. Millikan did. This is what R.A. Millikan did. That charge of no this thing so. No this thing so. R.A. Millikan in his oil drop experiment discovered that the charge of electron is what? Minus 1.6 times 10 to the power minus 19 what? Coulomb. That's what he did. Now, can someone tell me what we can get from this now? We have known the specific mass of. What is specific mass of? Specific charge of electron. Specific charge of electron is what? 1.76 times 10 to the power what? 11. Right? And the charge of electron, that one was according to who? J.J. Thompson, right? Now, R.A. Millikan now determine the charge of electron for us. And specific mass is what? Specific charge is what? Charge over what? Mass. So if charge over mass is what? 1.76 times 10 to the power what? Times 10 raised to the power what? 11 coulomb. Coulomb per what? Kilogram. And you know the charge of electron which is stand up. And you know the charge of electron which is 1.6 times 10 to the power what? Minus 11 coulomb. What can you deduce from this relationship now? And this is someone that thinks, I remember I told you something. As a class I told you, I mentioned something. I said, let me keep it. When we enter this structure, we'll talk about it. Who can remind me there's a figure I gave you sometime in the past. I say, don't worry, when we move forward further into the work of these scientists, we now conclude it. Who can remind me? Who can remind us? Nobody. I gave you the mass of electron in our last class. When I said that mass of electron is what? 9 point what? Check your notes now. You're looking at me. What I give you as mass of electron? When I said that the mass of electron is negligible. What they give as mass of electron? You've not seen it, or you didn't put it down. Hey, how can you in a class something we said you not put it down? You really see it in your own. Hey, Chinwe, is in your note? Ha! Now wow, doesn't make sense. So seriously, it makes no sense at all. How can I be saying something about you not put it down? Oh, wow. In our last class, I told you that mass of electron is 9.1 times 10 to the power what? minus 31 kilogram. Is that not what I told you in this class? I said the mass of electron is 9.1 times 10 raised to the power what? 31 what? Kilogram. 9.1 times 10 raised to the power what? Minus 31 what? Kilogram. That's why I told you that this minus 31, 10 to the power minus 31 is very, very small number. True or false? That is what? Negligible. That's why electron is not heavy. True or false? True or false? That one is reversed. So that they don't even put it, they put it in the mass as what? 0. True or false? Because of this mass of electron. I now said that when we go into the atomic structure proper, we will know how this thing was calculated. It was calculated from the work of R.A. Millikan and the work of J.J. what? Thompson. Because J.J. Thompson determined charge to mass ratio, which is what? Specific charge to be what? J.J. Thompson. Remember that specific charge. Specific what? Charge is equal to what? Charge over what? Over what? Mass. It's not true. And J.J. Thompson found this specific charge of electron to be what? 1.76 times 10 to the power what? Times 10 to the power minus what? 11 what? Coulomb per what? Kilogram. R.A. Millikan discovered the charge of what? Electron. You know, this sign that does contribute in the calculation. Hope you know. You show that it's a negative what? Charge. Hope you know. He now discovered the charge of electron to be what? Minus what? 1.6 times 10 to the power what? Minus 19 coulomb. Over mass. We don't know the mass of electron. So they make mass of electron this R. From this now, if you make mass the subject of the formula, you can determine the charge of what? The mass of what? Electron. Do it now and you get the answer. Just simply cross multiply and divide. That means the mass of electron now. Mass of what? Electron is now equal to what? This time, this divided by this, true of us is now what? Minus 1.6 times 10 raised to the power what? Minus 19 what? Coulomb. Over what? 1.76 times 10 raised to the power what? 11 coulomb per what? Kilogram. Coulomb will cancel kilogram. Look up. Coulomb will cancel kilogram. Here is per kilogram. So it will come up. True of us. Then divide. Do it now, fast. Tell me the answer. Divide it and tell me the answer. Don't worry. You use your calculator full. Do it fast so we can go. Are you now? Okay. Or use standard form and do it. Simple. Use standard form. Just divide this by this. Then minus 19 minus 11 should be what? Minus 19 minus 11 should be what? Minus 30. This divided by this will give you 0.9 something, right? And if you move the decimal point, it will add one more negative decimal. Here it becomes minus 31. Here it becomes 9.1 times 60 to the power what? Minus 31. Punch it. That's what it will give you. This is how they determine the mass of what? Electron. From the work of R.A. Millikan and the work of J.J. Thompson. This is how the mass of electron was. So if you punch this thing now, it will give you approximately 9.1 times 10 to the power what? Minus 31 what? Kilogram, which is the mass of what? Electron. Now, there's something I forgot to tell you. Thompson tried though. You see J.J. Thompson, he tried. No, the man tried. He laid a very solid foundation, even though he didn't succeed in atomic structure. Now, see what happened. Go back to that place know how you do it. I forgot to tell you about it. Know how you do it. That same time he discovered what? Electron. Am I communicating? Know how to do. He worked on electron. Know how to do it so that it will be a kind of continuation. Now see what happened. So with what he did with cathode rays and the pronouncement that they are electron, he was so happy. You know, if you succeed, you'll be happy, right? And you want to do more. He now continued. See what he did. He repeated the same experiment, but in this case, see what he did. Instead of using the one at the cathode here, I'm not forgetting. He used a discharge tube with a central what? Cathode. We are talking about discovery of proton. Okay? We are talking about how discovery of what? Proton. So that means Thompson did maybe that's why he now, who is that coming? Maybe that's why he get the mind. Listen carefully. Maybe that's why he got the mind and told us that an atom is composed of what? A sphere of what? Proton, in which electrons are embedded. Maybe that's what gave it the morale to tell us that kind of thing. Maybe after they work on electron and what? Proton, he now get mind and tell us that. But work of Gauge and Mass then prove him what? Wrong. So Rutherford sent his boys. Oh boy, please make us go check what this man did. If we allow this man now, he will take over the whole atomic structure. Go and check what he did, say whether it's correct. They now discover that no one will go there. We will now enter into Rutherford's work. Let's finish what he did in what? With what? Proton. Okay, let's continue. So, as I said, that instead of using discharge tube with cathode at end, right? Use the one with central what? Cathode. And the cathode has what? Holes. She's confused. If you see it now, she came late. She's confused. Why did you come late? Anyone that comes to my lesson late, I don't know. So sometimes I just pity them because I don't know what to do because I cannot go back. Unless after you listen to you go to my YouTube channel and listen to this because I don't have time again to post the link itself. Once you go to YouTube channel, you can see it there. Let's continue, please. So he repeated his earlier what? Experiment, but he used what? A discharge tube with what? A central what? Cathode that has a hole inside it. Now, when he noticed something else. Remember when he walked in, he noticed he glowed first, right? After, he now noticed what? Bright green what? Glow. In this case now, see what he noticed. He noticed a reddish glow. He repeated the experiment now, but he used one with cathode and what? Center, and the cathode has holes. He noticed something else. He noticed a he noticed a reddish glow now. Reddish one, red in color. Glow. That is, the one that is bright green is moving in this direction. The one that is what? Reddish glow is moving in what? Opposite what? Direction. Am I communicating? He noticed a reddish glow, but in opposite what? Direction to the one of what? Bright what? Green. That is the green glow. He now noticed, that's okay. If the one that is green is moving this way and is negatively charged, which he has already proven, right? The one that is moving in the other direction should be what? Positively what? Charged. That's where the issue of proton started coming up. Okay? You know, so the one that is moving in opposite direction is what? Positively what? Charged. Now, other experiments that were carried out later proved that this is actually what? Proton, okay? Now, they now put down some of the features. And the features are as follows. You're not writing anything. If you're easy. So why not writing? Because it looks as if I'm telling story, right? And the story I talk about up here. As he's sweeting you, please be putting it down. So you don't get carried away. I like how Kamsi is doing it. As the thing they sweet them, she put it down. So that when you have actually grabbed it, but when you now go back to what you have put down, it will stick more. And when you now open textbook and read it, man, you understand it well. You see how I'm breaking it down. Put it down. Listen. Put it down. Then after you go to the textbook and read it, you see that you don't even need to cram it. You understand it well. You all have this textbook, right? This textbook is one. This is new school chemistry for senior secondary school. This is our reference book. You all have it. Have you read this before? In it. Have you read this before? The topic there. Have you read? You don't even know the topic we are discussing. Who has read the topic here? The after now, go and read it now. You understand it. It will look like novel to you. We are talking about atomic structure. What you were here last week now? Yes. Hey, we continue from where we stopped. We didn't start from Dalton's atomic theory. We're moving. Now let's continue. So, the same way we talk about the features of the cathode rays, which are electrons. Now let's talk about the features of this positively charged rays. You know, if you put an opaque object in the path of cathode rays, what will happen? It will just cast the shadow, right? Right? But this positive ray causes deflection. You know what a deflection is? Deflection. You know what it means? To deflect something, right? Right? You know what a deflection is? To shift direction. If something is deflected, maybe it's moving like this, it moves the other way around. Okay? That's what's called deflection. Then when the it's well. Now listen. Now, unlike cathode rays now, these positively charged rays, they have what? Much larger magnetic field. They require larger magnetic what? Field. They require larger, how do I put it now? When you have okay, let me not go there. I'll break it down when I go to the charge. Now let's continue. So what actually happens is that they cause what? Deflection, basically. And for it to cause deflection, what comes to your mind? Who among you plays ball well? Okay, if you come with your ball and you want to attack me to collect the ball, or maybe the ball is moving like this, two of us are running towards that ball. I'll just let this. Just if you don't have you just fly, and it's like two of us. Your direction is to get the ball, and I'll just do that. Just like this or like this. You just fly and disappear. If you don't have strength, two of us, good. If you are so light, you just boom, disappear. No stamina, good. So that's what happens with what? Unlike cathode ray, that will just cast shadow, but this one will do what? Deflect. For you to do that, what do you think it has that can allow you to be able to do that? It's heavy, right? It's heavy, right? That's the word. It's what? Heavy. It's heavier than what? Electron. That's why it can cause what? Such deflection. And that's why it requires more larger what? It has very much what? Magnetic what? Field. So now that's exactly what happened. Now that's what they discovered. And that's okay. That means this is heavier than what? The one I discovered before is heavier than this. Two of us. Good. Remember the mass of electron is what? Negligible. Something that has 9.1 times 10 to the power around 31. What can it do? It just add. Even air has weight. What can it do? It can only cast a shadow. It can't do anything again. But this one will deflect. Proton, this positive charge, you know, they not call it proton that time. These positive charge rays have what? Weight. And they are heavier than what? Electron. Now, remember what I told you. Remember what I told you when we were discussing the features of electron, the cathode ray. We said that the cathode rays, they have the same nature, right? They have the same nature and the same specific charge. That is charge to mass ratio, irrespective of the cathode and nature of the what? Gas in the what too. Remember? Good. But unlike cathode rays, these positive charge rays, they are not like that. Listen, they are not like that. The mass depend on the mass of this positive charge is not at the bottom. Depend on the nature of the gas in the discharge tube. Okay, that's another feature. The mass of this positively charged rays depend on the nature of the gas in the tube. Are we together? I'm going to cheer out. There is a good in there. I'm going to do water. You swear. Now, remember I told you that it depends on the what? The mass depends on the what? The gas in the tube. That means they now use different gases. Okay? And they realized. J.J. Thompson realized, not even they, that when hydrogen gas is used in this tube, the mass of the positive charged particle produced is the what? The lightest, or the one at the least mass. When hydrogen gas is, you know that it depends on the weight, the mass, depends on the nature of the gas in the tube. Now, when they now use other gases, but when hydrogen gas is used, they realize that the hydrogen gas will produce positively charged rays with the least what? Lowest what? Mass. With the what? Lowest what? Mass. And if you check, what is the mass of hydrogen gas? Hydrogen as an atom, basically, is what? 1.008. True or false? Or just call it 1. True or false? True or false? Is it 2 or 1? Let's continue. Don't worry, we'll get there. But when we go into atom properly, atomic number, mass number, we are still talking about the discovery. But hydrogen is it 2 or 1? Is it 2? We have different other isotopes, hope you know. We have hydrogen, is it deuterium, deuterium, right? The one that has 2. We have the one that has 3. Remember I told you that the relative atomic mass is, you check their percentage abundance for each of them, and you find a percentage of the mass number and add it up. But when they add up, they got 1.008. I think so.
Atomic mass and weight of atomic mass.
Yes.
So does it have a formula?
The formula for relative atomic mass. That is from the isotopes. We have done that here. You missed it. You came late. Did you do the assignment?
Yes.
I did. There's a place you are given a calculation to calculate.
Yes, sir. What am I saying?
Did you calculate it?
Yes, sir.
I don't know the atomic mass now.
Sir, but there was the one as in the show atomic mass separate. I'm saying, for example, now that one to be got 1.008 in hydrogen. I'm saying, how did they get that?
That one I'm saying now is from the different abundance of all the isotopes that they use to calculate it. Okay? Yes. Now let's continue. So, when they now discover this, They say okay. He now named that one with the least what? Mass. What? Proton. Okay? They name it what? Proton. So that's why most times they'll tell you that have you noticed that they normally interchange hydrogen this thing with proton? Have you noticed that? Have you noticed that? If you have gone through chemistry work for some time, you read that sometimes they normally take hydrogen atom to be what? Proton. Have you noticed that? You have not. Know it today. Have you noticed it? This is where it came from. That is if you're not joking. You place too much. But for real, have you noticed it? Have you noticed it? For real. Now, when they use the hydrogen atom gave the what? Positive charge this thing with the least what? Mass. They now take it to be what? Proton. That was most times you see them saying that proton hydrogen atom is equivalent to what? Proton. Okay? Now, so this is exactly what happened. This is what J.J. Thompson did. So let's continue. So J.J. Thompson also discovered the same way he calculated specific charge for what? Electron. He also determined specific charge for what? For what? Proton. Okay? He also determined specific charge for what? Proton. And he got a specific charge for proton is what? He got it as what? 9.58 times 10 raised to power 7 coulomb per kilogram. Put it down. 9.58 times 10 raised to power 7 coulomb per kilogram. 9.58 times 10 raised to power go what? 7 coulomb per what? Kilogram. Are we together? Are we together? So, there's something else they did here. He now realized something. What is the specific charge of electron? 1.76, right? 1.76 times 10 raised to power what? 11 what? Coulomb per kilogram. Why specific charge of proton is what? 9.58 times 10 raised to power what? 7 coulomb per kilogram. So they now compare the two of them. The ratio of the charge of specific charge of electron to that of what? Of what? Proton. And realize that the charge of electron, proton, the specific charge of proton is 1,840 times less than the specific charge of what? Electron. Just divide specific charge of electron by specific charge of what? Proton. You will get 1,840. That's the ratio. So their ratio is what? 1,840 is to what? 1. Ratio of specific charge of what? Proton. Electron to specific charge of what? Electron is 1,840 is to what? 1. Is it clear? Is it clear? So that's how they got it. If you divide it now, but if you divide it, you get the answer. You get 1,840 is to 1. Is it clear? So that's what they got. But do you know why it happened? Do you know why it's like that? Do you know why the specific charge of electron is sit up. Do you know why the specific charge of electron? Go and sit well. Do you know what the specific charge of electron? Don't worry, we should end this class so you can rest. I think we stay for 2 hours, right? Do you know why the specific charge? Do you know what the specific charge? I think after this proton stuff will stop. Do you know what the specific charge of electron is? 1,840 times the specific charge of proton. Do you know why? Because electron mass, you know the specific charge is charged over what? mass. The mass of electron is so minute, it's negligible. And if you divide it, it won't even divide the what? Give you a subdivision of the what? Charge of what? Proton. Sorry, electron. But the charge of that of electron is proton is what? Mass is higher, right? If you divide it, it will bring it down. So they now say, okay, let's assume that the charge of electron is +1, -1. Charge of proton is what? 1. Let's assume that's an assumption. Let's assume that charge of proton is what? -1. Sorry, +1. Charge of electron is what? 1. That's what they now did and did the calculation and realized that proton is 1,840 times heavier than what? Electron. Okay? That way is what the proton is 1,840 times heavier than what? Than electron. So this is what J. Thompson did, and he was so happy. He did electron, successful. He now went into atomic structure and proposed and told us that an atom is, he forgot there's anything called neutrons. He didn't know that about neutron. He just said, because it was in 1932 that Chadwick discovered neutron. So to him, at that point in time, Rutherford, let me still your confusion. Rutherford, see what Rutherford did. There's what is called alpha scattering experiment. We'll still talk about it. Through his guys, Gege and Marsden. They now find out that there's something inside the center of the atom that is deflecting the rays they pass through, the alpha particles that is sent through to bombard the atom. There's something that is deflecting, that is opposite to the charge, that is deflecting it, and that it has weight and opposite charge. That's why it's deflecting. But they didn't go further to talk about neutron. It was Chadwick in 1932 that I came and called it what? Do more work on it and name it what? Neutron. They only saw there's something positive. That's what they said. That is moving the what? What they, you know that alpha particles is positively charged. So there's something inside that place that is repelling the positively charged alpha particle. If you enter it, you push it away. That means it has the same charge with it. They say that center is, they only say that the center is positively what? Charged. That's the only thing they said. And stop there. It was Chadwick in night. And this thing we are done, those works are around 1913, their own work. You know, Thompson was stopped with 1910. Around 1913, and Rutherford and his boys continued. So it was in 1932 that Chadwick now, don't worry, we'll talk about that one now. Or should we continue? No. Alright, to stop here. In our next class, I've already told you what led Thompson in 1898 to continue about what? Atomic structure. Telling us that the atom is made up of what? Positively charged sphere with negatively charged electron embedded in it. That's what he told us. But the work of Marsden and Gege proved it what? Wrong. We'll start from there. This will usher us into the work of Rutherford and his boys. That's where we started. Let me end with one statement Rutherford made. He said, statement he made about his boys. He said, I remembered Gege coming to me in a great excitement and saying, we have been able to get some alpha particles coming backwards. What does it mean? It was what? Repelled by the positively charged what? Nucleus. I will stop here. In our next class, I'll get a question to ask. No, wait, let's talk about it. You can search it anyway. You can search it too. Let's stop here. You say you're tired. All right. Any other question? In absence of any question, I think we'll stop here. Then rest. So when do we start? The time is 12:25. When do we start our physics, our mathematics class? The time is 12:25. 1:30. Do you agree?
Yes.
Eh? Do you agree? If you agree, let me see hands up. If you agree, Thompson said that we should start by 1:30. If you agree, let me see hands up. Just raise your hand. No, don't touch. Just raise your hand. If you agree. All of you agree. Alright, so we'll start by 1:30. Alright, thank you very much. God bless you.